Let's discuss the three laws of exponents and find conditions on which these are true and not true. First, the first one, um, z to the w1 times z to the w2 equals z to the w1 plus w2. This actually has the broadest range where it's true. This is true for any non-zero base, so z can be any complex number other than 0. And furthermore, w1 and w2 can be any complex number, period. And so this is true for pretty much any set of z, w1, and w2 as long as z does not equal 0. And even if z is equal to 0, there is a case where this theorem still applies if w1 and w2 are both positive real numbers. For example, 0 to the 4th times 0 to the 5th is equal to 0 to the 9th. The theorem breaks down if these conditions don't hold. So a counterexample, when these conditions don't apply, would be, say, something like this: 0 to the 2 times 0 to the minus 1 does not equal 0 to the 1st, because, for example, 0 to the minus 1 is not defined. So the first one is true for quite a range of values. Number 2, this law of exponents, z to the w1 raised to the w2 equals z to the w1 to the w2. This one is true as long as z is greater than 0 and w1 and w2 are real numbers. Now we proved this one in class. And just like we also proved in class that z can be a complex number, non-zero, and this would still hold true as long as w1 and w2 are both integers. Okay, so for the first example, z greater than 0, w1 and w2 both real numbers. A example where when neither of these work and it's still true, and the law of exponents is false, would be something like this: negative 1 to the third to the 1/2. Now this is equal to negative 1 to the third is negative 1, and negative 1 to the 1/2. Well, let's see, negative 1 is e to the I pi to the 1/2. And by definition of raising something to a fractional exponent, this is equal to e to the I pi over 2, which is equal to I. However, if I take negative 1 to the 3/2, that is equal to e to the I pi to the 3/2, which is by definition equal to e to the I pi to the 1/2 to the third. That's the way we do a fractional exponent when the numerator is not equal to 1. So this is equal to e to the I pi to the 1/2, we just got done saying is I to the third, and I to the third is negative I. So these, the claim here that the law of exponents is false, here I have a negative number, so the first rule doesn't apply, and both exponents are not integers, and so the second rule does not apply. Now, I did not prove this in class, and I wouldn't necessarily expect you to come up with this on your own, but there's another broad class where this works, and that is when z is any complex number. W1 can be any complex number, and W2 is restricted to be an integer. So this last one that I just wrote is we did not prove in class, but this is also true, that the law of exponents still works as long as the outside exponent W2 is an integer. Now, we did not prove this in class, but let's prove it here. Proof. So let's take a look at z to the W1, and let me switch letters to n to emphasize that the outside exponent is an integer. By definition, this is equal to e to the W1 log of z to the nth power. Okay, now there are three cases. Case 1. Well, first, the easy case, if n equals 0, then clearly the theorem is correct, right? If you have z to the W1 to the 0, anything to the 0 as long is equal to 1, and that's the same thing as z to the W1 times 0. So that's clearly correct. Case 2. Suppose n is a positive integer, then z to the W1 to the nth power is equal to, by definition, e to the W1 times the log of z to the nth power. Now we know full well how to raise things to integer exponents. So this is equal to e to the W1 log z times itself n times. And from a theorem in class, the exponential function, I have e to the x times e to the x, and so e to the x times e to the y is equal to e to the x plus y. So that's a theorem we proved in class. In other words, we're using the first law of exponents to simply add up the exponents. So we have e to the, if I add up the exponents, I get n times W1 times the log of z. And then by definition, this is equal to z raised to the W1 times n power. So that's case 2. Case 3, I'll do down here, is if z is less than, if n is less than 0, so in this case we let n be equal to negative m, where m is a positive number. Then let's take a look at this. So z to the W1 to the n is equal to z to the W1 to the negative m. By definition, that's equal to 1 over z to the W1 to the mth power. M is positive, and so I can write this as 1 over z to the W1 to the m. By definition, that is z to the negative W1 to the m. And negative m, of course, is n, so z to the W1 to the n. And so that is the end of the proof. So the theorem works, the law of exponents works for complex bases as long as the outside base is an integer. because I can appeal to the fact that e to the x times e to the y is equal to e to the x plus y, or that e to the z1 times e to the z2 is equal to e to the z1 plus z2, even if the base is a complex, even if the exponent is a complex number. Okay, so that's 1 and 2. The third law of exponents. Now, we did some work with the third law of exponents in class, so let me state what we did in class. In class, we showed that if w1 and w2 are greater than 0, and if z is a complex number, if z is a real number, then the third law of exponents is correct. We also showed in class that if w1 and w2 are complex numbers other than 0, and if z is an integer, positive or negative, then the third law of exponents is still correct. The canonical example where this fails is if I have something like negative 4 to the 1/2 times negative 9 to the 1/2. So note that this does not fall in either of the two cases. W1 and W2 are both negative, so we can't do that. And also, the W1 and W2 are certainly not 0, but the exponents z are real, are not integers. So that means that the second case does not apply. By definition, this is equal to 2i times 3i, which is negative 6. Also, we have that negative 4 times negative 9, whole thing to the 1/2, is equal to 36 to the 1/2, which is positive 6. And this little quirk about the square root function often appears in the secondary curriculum when the square root when complex numbers are first introduced. Students will recognize fairly quickly that the square root of negative 4 times negative 9 is equal to 6 and not negative 6, and then we'll ask the teacher what's happening here. What's happening is that the law of exponents is not always true if you have non-negative base. If you have a non-negative base. There is another case that we did not discuss in class where this is true, and I will show that now. And again, I would not necessarily have expected you to come up with this on your own. But if I permit the exponent to be a complex number, then the third law of exponents is still true as long as w1 and w2 are positive numbers. So to prove this, we first have a lemma. And the lemma goes like this. If I have e to the k to the z, so k is an integer, is a real number, and z is a complex number, then this is equal to e to the kz. And this happens anytime that k is a real number and z is a complex number. So the proof of the lemma is as follows. E to the k to the z. By definition of the exponential function, when I have a complex exponent, this is equal to e to the z times the log, the generalized logarithm of e to the k. Now, e to the k is a real number, and so the generalized logarithm of e to the k is exactly what you think it should be, the natural log of e to the k. And the natural log of e to the k is simply a k. And so that's the proof of the lemma. Now the proof of the theorem is as follows. It's going to cleverly use this lemma twice. Okay, so we're going to show that suppose we have x to the z times y to the z, where x and y are both real numbers. Now x can be written as e to the natural log x to the z power times e to the natural log y. Then that gets raised to the z power as well. By the lemma we just did, this is equal to e to the z natural log x and then e to the z natural log y. Now from the first law of exponents, we can write this as e to the z natural log x plus z natural log y. Now the z factors out, we get e to the z natural log x plus natural log y. Now from the ordinary laws of logarithms, that's e to the z times the natural log of x times y. And then using the lemma again, but this time in reverse. So we will take the k is going to be the natural log x here. So I can write this as e to the natural log x times y, whole thing to the z power, which is finally equal to, and I'm sorry for this mess here, x times y to the z. And so that's the end of the proof. So x to the z times y to the z is still equal to x times y raised to the z. So that rule works if z is a real number. We did that in class. And it still works even if the exponent is a complex number, so long as the two bases are positive numbers, so that you can take the natural log of the positive number. So that's the three law of exponents. I stated the rules that we proved in class, and for rules 2 and 3 I actually stated a generalization that we did not prove in class that I wouldn't necessarily expect you to have come up with on your own, but I trust you to be able to follow the proof.